All right, so lastly, I'm going to finish up this lecture with types of research claims. The idea is once you've established the variables you're interested in and you're happy with the effectiveness of your measurement, you want to ask yourself what's the goal here? So, what kind of research claim are you trying to make? Research claims break down most basically to the three listed here: your frequency claims, your association claims, and your causal claims. The idea is research is about trying to establish some new information that your data exhibits. You're trying to claim that you have found something. The different types of claims that you make, though, depend on the kinds of variables you're interested in and the kind of relationships between variables that you're trying to establish a claim for. Additionally, this frequency association to causal relates to the strength of the claims. Basically, it's easiest to make a frequency claim, it's hardest to make a causal claim. For your research projects, you're really going to be focusing on association claims because, as I'll get into, causal claims take a little bit more of an intensive research design. But I'm going to walk you through these three types. So the heart of a frequency claim is that you are evaluating the extent or quantity or frequency of one single variable. You're merely measuring how often or to what extent a variable exists. So examples of this would be social media usage. How often do people use Facebook or any other social media platform? How many people suffer from depression? The key thing in both of these examples is that it's a single variable and you're merely measuring the extent of the occurrence of that variable. So when you say 350 million people worldwide suffer from depression, the single variable is depression. The frequency claim is the number of people who suffer. Association claims are going to be when you're trying to link at least two variables together. What's going to make this an association versus a causal claim is that both of these variables will be measured. This is the distinction I mentioned earlier, whereby measuring variables are merely taking measurements of how much of a variable or the extent to which a variable exists, and you're not manipulating or changing anything about them. You're just measuring the extent that a variable is there. This is the heart of correlational claims. This is when you're trying to establish that certain variables covary or go together. Basically saying that as certain levels of one variable rise, so too do levels of a second variable rise. There's different qualities that a covarying relationship can take on: a positive, negative, or zero. Or I'm going to get into the interesting spurious association. So I'm going to walk through all of these individually. But the heart of an association claim is that basically you're assessing the extent to which level of one variable is associated with level of a second variable, right? Like depression and self-esteem. You know that those variables are associated. As levels of depression rise, you see levels of self-esteem diminish. When variables are associated in this way, they are, as we say, correlated, or they have covariance. So this is, again, going to be the kind of claim that culminates from correlational-based research. As I touched on earlier, you can visually inspect correlational relationships between variables via a scatter plot. That is, again, a visual that depicts data points, whereby placement along two axes tells you about that data point's levels of both variable A and variable B. So let's take a positive association, for example. This graphic depicts the relationship between individuals' height and their arm span. By visually assessing this scatter plot, you can tell a few things about the relationship between height and arm span. First, you can tell that that's a positive association because you see that slope of the data points is going upward from left to right. That tells you that as levels of arm span rise, so too do levels of height. That's a positive association. That relationship additionally appears quite strong, which you can tell because those dots appear to be making, like I've mentioned before, a kind of coherent linear or line-like shape. They appear to be closely placed near that best fitted line through the middle of the dots. Again, that basically means that the dots are creating a clear, positively inclined strong relationship between those two variables. And you can just tell that by eyeballing the way that those dots look in the scatter plot. Again, this graphic basically depicts a positive relationship between height and arm span that's quite strong. That's not particularly interesting, right? People who are taller tend to have wider arm span. That relationship's not perfect. There are some people who are tall whose arm span is not particularly wide for their body. That's fine. That's still a very strong positive relationship. A negative relationship, on the other hand, is going to look more so like this, whereby the data points in that scatter plot pretty clearly are trending downwards from left to right. They are inclined downwards from left to right. So for this particular graphic that depicts hours spent playing video games against GPA, you would be able to visually inspect that relationship and evaluate that it's negative. Again, you're seeing a somewhat coherent linear shape whereby those dots appear to be traveling closely to that best fit line that goes right through the middle of the dots. That tells you that it's a decently strong relationship. Again, it's not perfect. There are some outliers where their GPA is maybe not so much associated with their amount of time spent playing video games. That just means it's not a perfect relationship. It's a relationship that has some association to it and definitely trends in the negative direction. If you have a scatter plot that looks like this, on the other hand, whereby it's just kind of a cloud, the best fit line that would go through this cloud of dots is completely horizontal with no slope whatsoever. That tells you that there is zero association, or that there is no correlation. So the relationship between IQ and shoe size, nothing there. So you can tell that by looking at the scatter plot and seeing that it's not really making any real coherent shape, it's just a blob. A spurious association, this is an interesting one. This is an association that appears when you analyze your data and when you visualize your data that is the result of either a fluky coincidence or some other third confounding variable that's causing two variables to appear to be associated when they're really not. So whenever I describe spurious associations, I like to link to this cool website here. You see that bottom right, tylervigan.com. He's got a whole series of these graphics depicting spurious associations. Basically a series of analyses where he finds significant correlations between two completely unrelated variables. This one is my personal favorite because national treasure and Oscar winner Nicolas Cage, if you can believe it, films that Nicolas Cage has appeared in are very strongly associated with drowning deaths by drowning in a pool. So years where there are more Nicolas Cage films, more people die by falling in a pool. You can see in that visual that that relationship is quite strong. So the question is there an association between Nicolas Cage films and drowning in a pool? You might think to yourself, Nicolas Cage films are so bad, people drown themselves in a pool. I would contest that Leaving Las Vegas and Moonstruck are classics, so I'm going to disagree with you. I think the more likely explanation is that this is just one of those fluky coincidences. You put enough variables into a bunch of analyses, eventually you're going to have something wonky come out that's not actually true. That is a spurious association. A spurious association is a relationship that appears in the data that is not actually the result of the variables truly being related to one another, whether by fluky coincidence or some other confounding variable pulling the strings of these two variables, causing them to appear to be related. That is a spurious association. So although an association claim is not the strongest type of research claim you can make, it's still very valuable. It's a great place to start. And both positive and negative associations can help you make predictions. For example, like I mentioned, depression and self-esteem are associated with one another. So if somebody is struggling with their self-esteem, you have some ability to predict that they might be vulnerable for depression. The stronger the association is, the more accurate the prediction is going to be, right? If you look in the reverse, if someone is depressed, it's very much likely that they're also going to have low self-esteem. So the stronger the associations are, the more likely you're able to make predictions. But what it doesn't do is tell you about the causal relationship between your variables. So, like I mentioned, if someone has low self esteem, you might have reason to suspect that they will be vulnerable to depression. That does not mean that low self esteem causes depression. There's probably some other factor in people's psychological lives that causes both self esteem and depression to co vary. Associations do not tell you about causality. Your classic correlation doesn't equal causation. Correlation does not rule out causality. Maybe self esteem does cause depression, but you just can't know that if you're ultimately doing a correlational study. So make sure not to conflate association claims with causal claims. So, how do you actually make a causal claim? As I mentioned, this is the strongest research claim because it comes about from the most stringent and rigorous research method. A causal claim is going to be, again, multiple variables are at play, but you're claiming that one causes changes to the other. Again, this is a bold claim to make, and it requires a more stringent testing approach. It requires what we call an experiment. Now, this is not an experiment in the colloquial sense that people use to refer to any sort of data collection. An experiment in research methods terms is where at least one variable is manipulated. So this is going to be where researchers actively change something about the variable. So to use the self-esteem and depression example, to manipulate self-esteem, the researcher might give some participants a self-esteem boost and other participants a neutral control topic to read about. The idea is if the people who received the self-esteem boost are different from the control group in some way, you have an indication that self-esteem might be causing that change. Okay, so in order to make a causal claim, you have to do an experiment that involves the manipulation of at least one variable. A classic example of an important experimental paradigm is going to be your treatment versus your control group condition. In order to test the effectiveness of any sort of a treatment, be it a medical treatment or a therapeutic treatment, randomly controlled trials are done to evaluate the effectiveness of that treatment. So in order to do this, participants are either put into the treatment group or into a control group. The best experimental design will have participants being randomly assigned into treatment versus control groups, meaning that all participants have an equal chance of being in one group versus the other. The idea is that if my treatment group, after a certain time period, are significantly better than the control group, I have evidence that treatment caused improved outcomes. The control group is meant to be similar to the treatment group in every way, except that they got the treatment and the control group didn't. Only then do you have the most rigorous research method that lets you make that strongest research claim. A nice shorthand of words that you can use to give you an indication that something would be association versus causal. It's important to note that the language should accurately reflect the strength of the research claim. So if something is ultimately a correlation, it's important to use language that reflects that, like the first variable is correlated with the second, or is linked to, or is associated with, or may predict. The language is a little bit softer and it hedges just a little bit more because, again, an association claim is not quite as strong as a causal claim. Unless you're doing an experiment, I would caution you to avoid the causal claim verbs like causes, affects, exacerbates, promotes. This sort of language communicates to the reader that you did do an experiment, so it's important that that language is reserved for experimental designs that merit causal claims. Additionally, I would recommend when you're reading about research, whether in an academic journal or in more mainstream sources, look at how the language is subtly tweaked to try and cause the audience to come to a different conclusion. Are you reading about correlational research that uses a causal claim type of a verb? That might be an indication that you want to slightly reserve your judgment and think about why the authors might be using that misleading language. And you certainly, I recommend that you use your words thoughtfully in ways that actually accurately reflect the kind of research that was done. Okay, so I'm going to leave it there for now. I hope you guys are doing well, and I'll talk to you soon.